Hello everyone, welcome back to another measurement lesson. Today we're going to be looking at a broad range of measurement problems and how they could appear in your exams. Let's have a look at our concept map for today. Cool guys, so first things first, I'm going to remind you what a polyhedron is. I'm then going to revise the definitions of surface area and volume, and then I'm going to actually define the surface area and volume of a hemisphere. After that, we're going to look into some examples which involve combined shapes. Let's go to the first definition. So, a polyhedron is a three-dimensional figure with four or more flat surfaces. So at this point, I'm just going to pause. Just a reminder, a polyhedron is an actual three-dimensional shape. It's a shape that I could possibly hold. So it could be a spherical ball, it could be a box of chocolates. It's not two-dimensional, because two-dimensional refers to a shape that could be drawn on a flat surface. So if I were to draw a triangle on a piece of paper, that would be a two-dimensional triangle. Cool, let's go to the next definition. So the surface area can be defined or explained as the total surface area of a polyhedron, and we know that a polyhedron is a three-dimensional shape, can be found by adding together the areas of each face of a polyhedron together. So everyone, the surface area has got to do with the area that the three-dimensional figure has on its outer surface. So if I had a cube and I wanted the surface area of the cube, I know that the exterior of a cube is made up of 6 external squares. So if I were to find the surface area of a cube, I would have to find the area of all 6 squares and add them together, because that will be the total surface area of that cube. Let's go to the next slide. So volume. The volume of a three-dimensional shape refers to the capacity that the shape has. The volume of a three-dimensional shape is determined by working out the area of the base of the object, and then it is multiplied by the perpendicular height. If you've tuned in before, you know I've always made a fuss about the fact that we have to multiply the base by the perpendicular height. So the height that involves a right angle, because that will give me an indication of the capacity of the polyhedron. Great, let's go to the next slide. Another thing that comes into play in measurement is scale factors. So for scale factors, we can say that it is possible that the dimensions of a prism are changed by a certain factor. The number that each dimension is multiplied by is known as the scale factor. Often we refer to the scale factor as a scale factor of k. Continuing on that note about scale factors, in general, if the dimensions of a regular polyhedron are changed by a factor of k, then please note that the surface area is changed by k squared and the volume is changed by k cubed. So please note there are some exceptions to this trend. So there are some cases where it won't be the surface area multiplied by k squared and the volume by k cubed. But in general, when I've changed my dimensions by a scale factor of k, the surface area changes by k squared and the volume by k cubed. Cool, just some advice for problems involving combined shapes. For measurement problems, it is crucial to consider the words of the question carefully, because often hidden clues how to solve my problem are involved in how my question is phrased. Also just want to say, please pay special attention to any indication that any shapes, surface areas, or volumes that have been removed from the whole. So for instance, if you have a box, but I've told you that I've taken the top of the box off, that would have an impact on the surface area. So please just be aware of what's included and what is not included. Lastly, it is very important to visualize the problem. So most measurement examples are based on real life scenarios. So it can almost help to visually picture in our brains how this problem has come about, because that could give us some indication on how to solve it. Great, everyone. I hope that you're with me so far. All that I've done up till this point is just revise some important measurement concepts that can help me solve problems. Let's go to the next slide. So we are now going to define the surface area of a hemisphere. So we can see that a hemisphere is half of a sphere. But if I'm thinking about the surface area of it, it's going to be half the surface area of a sphere, because I can see it's half of a sphere. But I also have to account for the fact that I'm adding the area of one circle as well. So the surface area of a sphere is 4 pi r squared. And then I also am adding the area of this top circle. And I know that the area of a circle is pi r squared. So half times 4 pi r squared gives me 2 pi r squared. And I'm adding this to pi r squared. So I can simplify and say that the surface area of a hemisphere is equal to 3 pi r squared. Great. Now let us define the volume of a hemisphere. So the volume, I don't know why there's an area there, so the volume of a hemisphere is going to be equal to a half times the volume of a sphere. Because if a sphere has a certain capacity, and I'm now taking a hemisphere, that is half of the capacity of the sphere. So it's going to be a half times the volume of a sphere. And I know that the volume of a sphere is 4 over 3 pi r cubed. So if I want to simplify this, I can cross cancel my 2's. So the volume of a hemisphere will be 2/3 pi r cubed. Great, so I'm quickly going to show you an example of how this can apply. So if we are given the following hemisphere with a diameter of 11 centimeters, we can determine the surface area of the hemisphere, and we can determine the volume of the hemisphere. Great, so let us do A. So we are first going to be calculating the surface area of this hemisphere. Please note that I've given you the diameter as 11 centimeters, but my formula calls for the radius. So that means that my radius will have to be half of my diameter, which is going to be 5,5 centimeters. So at this point, I can fill it into my formula, because it's going to be 3 pi times 5,5 squared. So let's pop this into my calculator. 3 pi times 5,5 squared. So the surface area is going to be 285, and I can see if I round off to the second decimal place, it's actually going to become 285,1. 1 centimeters squared. It remains squared because it is surface area. Now let's do the volume. Again, just a reminder, we've said that the radius will be 5,5 centimeters because I have halved my diameter. So now I can fill it into the volume formula. So it's going to be 2/3 pi times my radius cubed. It's cubed, but now because we're working with volume, so let's just plug this all in. We've got 2 over 3 multiplied by pi times my radius cubed, which is going to give me 348,45. And this will be in terms of centimeters cubed, as it is a volume. Great, everyone. I hope that you're with me so far. After the break, we're going to look at some more examples. See you soon. Hello everyone, welcome back. Before the break, I had started to revise some measurement concepts, and I also defined the volume and the surface area of a hemisphere. Now, in this portion of the lesson, we're going to be looking at some examples. Let's go to the board. Cool, so the first question says that the diagram shows a cone with a perpendicular height of h centimeters, a radius of r centimeters, and a slant height of 13 centimeters. Here we can see that we have two missing variables. I don't know what my h is, and I do not know what my r is. Okay, so A is asking me to show that the volume of the cone is given by V is equal to 169 pi h minus pi h cubed over 3. Then B is asking me if h is 12 centimeters, determine the total surface area of the cone. So we're going to start with A. And we can see that we have to express the volume in terms of pi and h, because those are what are present, and we know that our end goal is to have volume expressed as this. But if I look at my volume formula for a cone, we can see that it is pi r squared h. So in our end goal, we can see that there aren't any r's included. So that means I'm going to have to find another way to express r. So looking at my diagram, we can see that I have a right angled triangle. And the second that I have a right angled triangle, we need to be thinking how Pythagoras could be helping me. So if I want to express r in terms of h and 13, I could do that using Pythagoras. So r squared will be equal to 13 squared minus my h squared because of Pythagoras. And because I want r by itself, we know that r will be equal to the square root of 169 minus h squared. So that will be r. So now all that I'm going to do in this case is I'm going to replace my expression for r into the volume formula. So I'm going to write it over here. So the volume will be equal to 1/3 pi times my radius, which I've written as the square root of 169 minus h squared. This will be squared and multiplied by h. So the volume will be 1/3 pi. Now just a reminder, when I square something that is under a square root, it just returns to becoming its original form. So this will just be 169 minus h squared, and this is being multiplied by h. In my next step, I'm just going to bring my h to the front, because then I will be able to distribute 1/3 h pi, or 1/3 pi h rather, into my bracket. Because if I do distribute it, I'm going to be left with 169 pi h over 3 minus pi h cubed over 3. And I can see I have arrived at my end goal. So essentially all that I needed to do is express r in terms of h, and that helped me find the volume. Great everyone, I hope that you're with me so far. Just for any of these questions where it's a show that, please let the answer or the end goal or what you're supposed to end up with guide you, as this can help you with your steps in the problems. Let's do B together. So we now need to determine the total surface area of the cone. The surface area of the cone can be found by saying pi r times the length of the cone plus pi r squared. So please note that this length is referring to my slant height, which I do have. But please will you note that it's now being given that the perpendicular height of the cone is 12 centimeters. So this is particularly helpful because now with this being 12 centimeters, I can actually do Pythagoras to work out what my r is, as I do need my r to fill into my surface area formula. So let's calculate r. We know that r squared will be equal to 13 squared minus 12 squared because of Pythag, Cool? Which means that r squared will be equal to 169 minus 144. So r squared is equal to 25, and if I square root that, I can see that my radius is 5 centimeters. So I can now substitute into my surface area formula. It's going to be pi times 5 times my slant height, which is 13, plus pi times r squared, which will be 5 squared. Now we can plug this all into my calculator to determine the surface area. So it's going to be pi times 5 times 13 plus pi times 5 squared, which I know is 25. So the surface area is going to be 282,74. And I know that my answer will be in terms of centimeters squared, as it is a surface area. Great, everyone. I hope that you're still with me. We're now going to take a look at another example. So, the diagram shows a pyramid with a square base and vertex A. The side length of the base is 16 centimeters. P lies on the square base directly below A. So we can see on our diagram that we've got a right angle and P is directly below A. The volume of the pyramid is given to be 640 centimeters cubed. So now that we have our introductory information, we've got our square base pyramid, and now I'm going to see what questions they actually want to ask me about it. So let's go to the next slide. We're first going to show that the perpendicular height of the pyramid AP is 7,5 centimeters. Then we're going to determine the total surface area of the pyramid. So let's go to A. Cool. So we need to determine that the perpendicular height is 7,5 centimeters. So that means I'm trying to find out this portion of the formula. The volume of a pyramid is equal to 1/3 times the area of the base multiplied by the perpendicular height. So I want AP, which is my perpendicular height. But luckily in this case, I was actually told what my volume is. I know that my volume is 640 centimeters cubed. This will be equal to 1/3 times the area of my base multiplied by my perpendicular height, which is my missing piece of information. But what is the area of my base? I can see that it is a square-based pyramid, which means that all of these lengths are 16 centimeters. But because I know that information, that means that the area of the base will just be length times breadth, which is 16 times 16, because it is a square base. So at this point, all that I need to do is isolate my height. So I'm going to get my calculator out. And if I want to isolate my height, I'm going to have to say 640 divided by 1/3 times 16 times 16. So I'm first going to say 1/3. Sorry, this fraction button is not my friend today, guys. Don't worry. There we go. Now it's working for us. So 1/3 times 16 times 16, which is going to give me 85,3 recurring, but I know I have to divide 640 by that in order to get my height. So I'm going to say 640 divided by my previous answer gives me 7,5. So 7,5 is my perpendicular height, which was the goal that I had at the beginning. Great, so now that we know what our perpendicular height is, I could go on to the second part of the question, which is B. Let's go to B. So we know that the side lengths of the square base are 16 centimeters each. We've now proven that the perpendicular height is 7,5 centimeters. So this height is 7,5 centimeters. Now we want to determine the total surface area of this pyramid. Cool. So what we're going to do is we're first going to find the area of the base, and then we're going to add it to the particular triangles that make up the exterior of this pyramid. But before I do that, I'm actually just going to remind you guys that when I'm working with surface area, the height is referring to my slant height. So I need this particular height in order to calculate the surface area of the pyramid. So I know that my perpendicular height is 7,5, but I'm going to need my slant height for the surface area. So I'm going to have to use Pythagoras in order to find my slant height. So because we know that P goes directly from A down to the middle of this square, PT will be equal to 8 centimeters. So when I'm working out my slant height, I'm going to use Pythagoras. So I know that my slant height will be equal to, my slant height squared will be equal to 8 squared plus 7,5 squared. So I'm going to put this in my calculator. So we've got 8 squared plus 7,5 squared. But I know that I'm going to have to square root my answer in order to establish what my slant height is. So I'm going to square root my previous answer, and I'm going to get that my slant height is 10,97. So now I can actually plug everything into my surface area formula, because I'm going to have the area of my base, which is 16 times 16, plus 2 times the triangles that connect to the base. So it's going to be a half times my base, which is 16, times my slant height, which is 10,97. And then I'm going to add this again. I'm going to just come under here, guys, because I'm going to run out of space, plus 2 times a half times my length, which is 16, again multiplied by my slant height. So now I need to plug this all into my calculator, because that will give me my answer for surface area. So it's going to be 16 times 16 plus 2 times a half multiplied by 16 multiplied by 10,97 plus 2 times a half multiplied by 16 multiplied by 10,97. And guys, if you're wondering what these plus 2 half times 16 times 10,97, all that I'm doing is I'm adding the triangles that make up the exterior of the surface area together in order to establish the surface area. Because for the surface area, I need the area of the base, and then I add that to the area of the 4 triangles that make up the rest of this pyramid. So the surface area will be 607,04. So guys, the surface area of this particular pyramid is 607,04 centimeters squared. Welcome back, everyone. In this segment of the lesson, I'm going to remind you again of the definitions of volume and surface area. After that, we're going to dive into some more examples. Let's go to the first definition. So, just a reminder about surface area. We know that the total surface area of a polyhedron can be found by adding together the areas of each face of a polyhedron together. So I know that often a three-dimensional shape is made up of different shapes, or the exterior is made up of different shapes, but the surface area has got to do with the total area of the exterior of the particular shape. And by finding the total area of the exterior, that is my surface area. Let's go to the next slide. Cool. The volume of a three-dimensional shape refers to the capacity that the shape has. The volume of a three-dimensional shape is determined by first working out the area of the base. And once I have the area of the base of the object, I then multiply it by its perpendicular height. Please make sure that you have the perpendicular height for volume and not the slant height. Cool, guys, let's go to our first example. So we have been given a spherical glass ball that has been tightly packed into a box. The box is in the shape of a cube. As shown in the picture, the radius of the ball is 6 centimeters. The second diagram shows the cross-section of the glass ball placed inside the box. We want to know what volume of the box remains after the glass ball is placed into it. So essentially, everyone, we have a glass ball that has been just squeezed into a box. And I want to know, with this glass ball in the box, what is the volume of the empty space left over? So the ball is sitting in the box, but I want to know how much space is actually left inside this box. So how are we going to do that? I'm going to let you guys think for a moment. So if we're working with volume, what I'm actually going to have to find out is what is the actual volume of the box and what is the volume of my actual ball, of the glass ball. Because then I can take the area of the box and subtract, sorry, not the area, I'm going to take the volume of the box and then I can subtract the volume of the ball. And that will let me know how much empty space is left. Let's go back to the board. So we are first going to look at the volume of the ball. And I know that the volume of the sphere is 4/3 pi r squared. And I actually know what my r is because I've been given it as 6 centimeters. So I'm going to fill that in. So it's going to be 4/3 pi times my radius squared. So let's pop this into my calculator. So it is 4/3 multiplied by pi multiplied by 6 squared, which is going to give me 150,8, because if I round to the second decimal place, that 796 will become 8. So 150,8, and we know it's centimeters cubed because it is in fact volume. Now we're going to work out the volume of the box, and the volume of the box will be determined by the dimensions of the box. But I can see that if the radius is 6 centimeters, that means that this entire length will be 12 centimeters. And as it is a cube, that means that each length will be 12 centimeters, 12 centimeters, 12 centimeters. And the volume of a box, we know, is taken by finding the area of the base and multiplying it by the height. But as it is a cube, each of these lengths is actually the same. So the volume of a box is length cubed. And then if I substitute in 12, it's going to be 12 cubed. So we're going to find that in our calculator. So 12 to the power of 3 is going to give me 1,728. So I'm going to carry this across so that I can actually determine how much of the box is empty. Cool. So we know that the volume of the space left over will be the volume of the entire box, and then we're going to subtract the volume of the ball. So the volume of the box is 1,728, and I'm going to subtract the volume of the ball, which is 150,8. So I'm going to plug this all into my calculator. So 1,728 minus 150,8 comma 8, which is going to give me 1,577, comma 2. And we know it's going to be centimeters cubed because it is a volume calculation. Great, guys. So after the break, we're going to be looking at some more measurement examples. See you soon. Welcome back, everyone. Before the break, I revised the definitions of surface area and volume. In this part of the lesson, we're going to dive into some more examples that can help us have better ways of solving measurement problems. Let's have a look at the concept map. So guys, we're going to look at how measurement assists us in problem solving with shapes. We're also going to look at strategies for measurement problem solving, and we're also going to see that there are some links between trig and measurement questions. So we are first going to have a look at this question. So the diagram shows a water tank which is made up of a cylinder and a cone having equal radii. So when it says equal radii, that just means that the cylinder has a radius of 0,5 meters and the cone has a radius of 0,5 meters. The angle between the perpendicular height AB and the slant height AC of the conical section is 35,5 degrees. So that is this top angle that is labeled over here. We know that this angle is 35,5 degrees. The first thing that we are going to be working with is calculating the perpendicular height of the cone. So traditionally, when I see the words perpendicular height, I often end up thinking, okay, well, this means that I'm probably going to be using Pythagoras, because we know Pythagoras is a common way to find the side of a right-angled triangle. But in this particular example, I see that I only have my angle and a side. But I'm hoping that we can draw on previous knowledge, and this is one of the examples where different sections of maths intersect each other. It is fairly common, if you look at certain past papers, that trigonometry sneaks its way into measurement, especially with regards to a right-angled triangle, because I know that I can use my trig ratios to find missing sides. So always just a reminder, when I am using trig ratios, I have to label my sides relative to the angle that's given. So I can see that the opposite side is 0,5, the adjacent side is AB, and my hypotenuse is AC. I want to find AB. So I'm looking for my adjacent, and I have my opposite. So if I think about my trig ratio, so a lot of people say SOHCAHTOA to remember it. Different people remember it in different ways. You can do whatever your teacher has taught you. But the trig ratio that involves the opposite and the adjacent is tan. So tan 35,5 degrees will be equal to my opposite, which is 0,5, over my adjacent, which is AB. But I want to isolate AB. So in order to isolate AB, I'm going to multiply both sides by AB. So I'm going to have AB tan 35,5 degrees is equal to 0,5. But to get AB by itself, I have to divide both sides by tan 35,5. So AB will be equal to 0,5 over tan 35,5 degrees. Now I'm going to use my calculator to actually work this out. So I've got 0,5 over, sorry that we can see we've got a bracket missing over there, 0,5 over tan 35,5 degrees, which is going to give me 0,7. We can see later on there's a 9 involved, but because I'm rounding to the second decimal place, I'm going to say that my perpendicular height is 0,7 meters. So we know this is 0,7. Great, guys, let's go on to the next question. So, when the tank is full, an electricity pump switches on and pumps the water from all of the tanks into an irrigation system at a rate of 0,52 meters cubed per hour. The pump automatically switches off the tank when it is a quarter full. We are going to be calculating how long in hours the pump feeds water into the irrigation system. So guys, we're going to be working with the volume of the tank. So before we can actually dive into the irrigation system, I'm going to actually have to know my volume. Let's go back to the board. So the height of the tank itself is 1,8 meters, but I calculated the length of my perpendicular height. So I know that my perpendicular height is 0,7, but because my perpendicular height is 0,7, that means that the height of the cylinder would have to be 1,1 meters, because we know that from this point going up, there's a height gain of 0,7. So we know that the radius is 0,5. We've got that angle. We also know the rate of pumping until it's a quarter full. So we need to calculate the time in hours, but I'm first going to have to calculate the volume of my cone before I can move on. The volume of a cone is normally said to be a third times pi times r squared multiplied by the perpendicular height. But I can actually work this out by filling in what I know. So it's going to be a third times pi times my radius squared, which is 0,5 squared, multiplied by my height, which I found earlier is 0,7. So I can now plug this all into my calculator. So it's going to be a third multiplied by pi multiplied by 0.5 squared multiplied by 0,7. And this is going to give me an answer of 0,18. So the volume of the cone is this is going to be a cubed because it's a volume, 0,18 meters cubed. Great, so now let's move on to the next calculation, and that is going to be the volume of my cylinder. I know what my volume of my cone is, but now it's time to do the cylinder. And the volume of a cylinder is pi times r squared multiplied by my height. But I discussed on the previous slide that we know that the height of my cylinder is now 1,1 meters because I know that the height of the cone on top is 0,7. So the height of my cylinder is 1,1. So it's going to be pi times my radius squared. I know my radius is 0,5 multiplied by my height, which is 1,1. So sorry, I forgot the squared in there. So it's pi r squared multiplied by my height. So let's fill it into my calculator. So it's a pi multiplied by 0,5 squared multiplied by my height, which is 1,1, which is going to give me an answer of 0,86. So the volume of my cylinder is 0,86 meters cubed. And my answer is cubed because it is a capacity, it is a volume, so my units have to be cubed. So now at this point, we have the volume of my cone and we have the volume of my cylinder. So we know that the rate of my pumping is 0,52 meters cubed per hour until it is a quarter full. So we want to know that we've worked out the volume of the cone and the volume of the cylinder. So the total volume of the tank would be 0,18, the volume of the cone, plus the volume of the cylinder, which is 0,86. So the total volume of the tank is 1,04 meters cubed. But we want to know how much of the volume that is going to be empty, because we want to know the rate of pumping until it is a quarter full. So we want to know the time in hours until 3/4 of it hasn't been reached yet. So it's going to be 3/4 multiplied by 1,04. So we're going to have 3/4 multiplied by 1,04, which is going to give me 0,78. And I want to know the time in hours that this takes. So I'm going to have to divide this by the rate of pumping. So we know that the volume of the water pumped is 0,78 meters cubed, and I'm going to have to divide that by the rate of pumping. So it's going to be 0,78 meters cubed divided by the pump of rating. So let's pop that all into my calculator. So it's going to be 0,78 divided by 0,52, which is going to give me an answer of 1.5 hours. Great, everyone. I hope that you're still with me. We're going to go on to another example. Cool. So the diagram represents a design that a chocolate factory wishes to use. So the diameter of the cone is 40 millimeters and its height is 50 millimeters. So that is this particular cone in this diagram. The first cylinder has a radius of 35 millimeters, the second cylinder has a radius of 25 millimeters, and the height of the cylinder is 10 millimeters. We want to determine the total volume of chocolate that is required for each chocolate model. So guys, we just need to picture this. We've got a cone and we want to fill this entire cone with chocolate. We then have two cylinders that are sitting inside each other. However, I'm filling chocolate in this circular mold. So we've got the larger cylinder on the outside, which is cylinder 1, and then I've got the smaller cylinder on the inside, which is cylinder 2. So I'm filling chocolate in between the two cylinders. So I'm not counting this middle space. So you can almost see that it's just a circular ring of chocolate that's going to be made. But if I'm going to determine the total volume of chocolate needed for all of the models, I'm going to have to break this example up into different pieces. Great, guys. So I know I've got certain molds that I need to fill with chocolate. I'm going to be filling the cone with chocolate. So I'm going to first have to actually work out the volume of that cone. Then the next calculation is it's slightly more intricate because I have a cylinder within a cylinder. I need to work out the volume of the larger cylinder on the outside, and I'm going to have to subtract the volume of the smaller cylinder on the inside, because the difference between those two will leave me with that ring of chocolate that will be in the volume of the difference between the bigger and the smaller cylinder. So we've got a few volume calculations to do. Also, please note that this question has asked us to leave our answers in terms of pi. So I'm not going to stress about decimals. For this particular example, I'm going to leave my answers in terms of pi. Let's go back to the board. So first things first, we are going to calculate the volume of the cone, and the volume of the cone is going to be 1/3 times pi r squared times the height. So it's going to be 1/3 times pi times my radius. So please note I've been given the diameter of the cone. That means that my radius will be half of this. So my radius will be 20 millimeters. So it's going to be 1/3 pi times 20 squared multiplied by my height, which is 50. So let's plug this all into our calculator, friend. So it's going to be 1/3 multiplied by pi multiplied by 20 squared multiplied by 50, which we know we're leaving our answer in terms of pi, so it's 20,000 over 3 pi. And that is the volume of the cone. Now we're going to look at the volume of the chocolate that's going to be between the two cylinders. So the volume of cylinder 1. So cylinder 1 is this larger cylinder on the outside. And I'm going to find the volume of that cylinder by substituting into pi r squared h. So it's going to be pi times my radius, which is 35 squared, and I've been told that the height of the cylinder is 10. So this is cylinder 1, so I'm now going to plug this all into my calculator. So it's pi r squared, which is 35 squared, multiplied by my height of 10, which is going to give me 12,250 pi. Cool, so that is the volume of cylinder 1. Now I need the volume of cylinder 2. So the volume of cylinder 2 is going to be dependent on the radius of 25 millimeters. So it's the same formula, except now we know we've got a smaller radius of 25. I'm going to plug this all into my calculator again. So it's pi times my radius squared multiplied by 10, which is going to give me 6,250 pi. Now to put this all together, we have the total volume of the chocolate required. So we first got the volume of our cone, which we got to be 20,000 over 3 pi. Then I'm going to have to figure out the chocolate that's going to be filled in between these two cylinders. And that is going to be the volume of the larger cylinder, cylinder 1, and I'm going to subtract the volume of the smaller cylinder, which is cylinder 2. Now I just need to plug this all into my calculator to see the volume of chocolate that will be required. So I'm going to have 20,000 over 3 pi, and this is going to be added to 12,250 pi minus 6,250 pi, which is going to give me 38,000 over 3 pi. And I know that all of my dimensions were in terms of millimeters cubed. Thank you so much, everyone, for joining me for today's lesson on measurements. I hope that it's helped, and I hope that you have a wonderful day further. Goodbye.